Hello, this is Al, and this here is my next attempt at adding a quick, hopefully very quick, simple entry into the references section so that we have something there, at least a couple things. Now I was just going to try to briefly explain the two functions, one for encoding and one for decoding UTF-8. UTF-8, as you probably should know by now, is a multi-byte format in which Unicode characters can be represented. That is, UTF-8 and Unicode 16-bit characters have a one-to-one. There is a one-to-one correspondence between a sequence of wide characters, 16-bit characters, and a Unicode UTF-8 multi-byte sequence, and so therefore you can encode Unicode as multi-byte. And why that is important, I've explained a few times, I think. I don't think I should have to go over it again, but essentially the byte is the smallest unit of data on a computer system. You might think it would be a bit, but in terms of storage, storage devices store bytes, not bits. Transmission might be in bits, but normally the things being transmitted are bytes. Okay. Now I've written out here, and this may seem confusing at first, a table that outlines how the UTF-8 encoding system works. So what I'd like to do is this bit, try and show you how to encode a wide character number, 16-bit number in UTF-8. Now, the encoding scheme is a variable length scheme, and that is a 16-bit number may be represented in UTF-8 as either 1, 2, or 3 bytes. Although that representation is unique, the length changes. For character values from 0 up to 7F, that's 127 decimal, only 1 byte is required to represent it. So that's what this first line is telling us. The way to read this is, if it so happens that you are looking at a stream of bytes and you know that the encoding is UTF-8, and you run into a byte, so a single byte, because it's multi-byte, and it has the value, let's say 1F something, okay? Then you can immediately say, without any ambiguity, that that corresponds to the Unicode character. I'll put 0 X's. Okay, that is now why is that? I mean, how can you tell just from 1 byte? Well, because there are 3 ranges, and you will notice that in the other ranges, okay, now the way to read this is X's are variables. X's are the number that you're trying to store. And these 1s and 0s are fixed. They represent the They represent the pattern of the structure of a particular encoding. And neither of these structures contain any bytes that have a 1 in the highest position. The high order bit is always 1 for these two and 0 for this one. This byte high order bit is a 0. It's easier maybe to see it in binary. In binary, this is 0, 0, 0, 1, 1, 1, 1, 1, right? So therefore the high order bit is a 0, so therefore it only matches this pattern. And the rule is that that number is the number, no matter how many bits you're using, represented by that character. Okay? Right? Now, so right away, this is an immediate consequence of the scheme. You can tell by just looking at one byte, in this case anyway, what its Unicode value would be. Now, if you saw another byte, suppose you saw a byte that did have a 1 in the first position. So let's do this in binary. It's easier. Maybe put a bar here or something. Keep them separated. Okay. Is that easier to read? I don't know. How about the spaces? Okay. Now, if we had, so here was example 1. Let me try another example. You'll see why they've chosen the way this pattern the way that they have. And at the same time, I'll be able to explain what the second line says. Let's suppose we run into a byte that looks like this. Yeah. All right. Well, first off, we know that it cannot be in the case A group, right? So we know that it's not finished. This does not correspond to any 16-bit number. And we know that because we know that it can't be in the first set, and so therefore it's either a 2-byte or a 3-byte encoding, part of a 2-byte or a 3-byte encoding. Okay. Can we tell which set it's in? Well, could it be possibly in this set? Well, if it were in this set, that would require 2 1s and a 0, right? So it couldn't be that doesn't have that property, and neither do these ones. So therefore it must be in the second set, and so therefore there must be one more byte that follows this one. So we know it must be one more byte, and it must have the 1 0 XXX 6 X's, 6 variable things that a person can place in. So it has to have that form. And so just by looking at this single byte, if we found a byte like that, we would know with 100% certainty that it is the first part of a 2-byte sequence, and therefore it corresponds to a number within the range 80 to 7FF. So we also know that. It's in this range. 0. No. 0. 80 to 7FF. Right? So that's what the second range goes from 80 to 7FF. So you can see that's good. What if we found a byte like this? Oops. I'm just making them up. That's 8. Okay. Now what does this tell us? Well, it certainly isn't in this group, right? But it could be in this group or this group, and we don't know. Because both of these possibilities have 1 0 followed by some arbitrary bits. So this one, we know that it must be within the first or second group, and we can't really, if we can't look backwards, we might not be able to figure out which group it's in. We certainly would not be able to determine what number goes with it. So we know what's 100% certainty. We know we cannot determine the value. Can't. It's in the middle of so this would be if there was some data corruption, let's say, and we lost a byte in a transmission, and we found this sitting on its own. It doesn't matter. We need to have seen something before this with this pattern or this pattern to determine not just which set it's in, but also the missing bits. Okay. Now, if we look at the next byte, right? So if we're in this scenario, next byte is going to be either, and we know this for sure, if it's case 2, then that would imply that the next byte is not of the 1 0 form. Can't be, right? Because if we're in the middle one here, then the next byte has to be the beginning of the next sequence, which means it has to be this form, or this form. Okay? So therefore, if the next byte is in this format, it has to be this type of the third part, the third sequence. And then the next byte after that has to be one of these again. So we can tell anyway. So we can tell from reading the next byte well, whether or not which of the cases it is, and hence we know where the start of the next sequence is just by reading the next byte. Okay? Similarly, well, that pretty much covers everything, right? Well, no. If we read one of these, if we suppose we read one of these things, and the next byte happens to be of one of these forms, then we can't tell about the past, but we still know that we're starting a new thing. So this scheme is good in several ways. In that there is a unique mapping in both directions, and it's a very simple pattern, as you can see, and any kind of data loss or failures in transmission are easily recoverable because we can always tell by looking at just one byte whether or not we're at the head of a new sequence or if we're in the middle. And if we're in the middle, we know where the next sequence begins because these patterns don't occur following. So that's one of the good things about the way it was designed. Okay, so now all you do, I gave you one example. Let's take an example in this range and see how to encode. Maybe it's best if I use my random little thing in here. %rand. Now I can get random numbers like that, and they're not. Okay. How about this? $3DFO. No, that's too far. Maybe if I divide my random, I can't really divide. Can I? Well, no, I could. 2x %random divided by, let's say, 10 hex. That should work. I'll get a number. That should convert it to hex. That fits. 62F. Just so I don't, So let's see if we can figure out what that would have to be in UTF-8. 62F. Now, so that's in this range, right? It's bigger than 80 and less than 7FF. So therefore, the result is going to have this pattern. First, we want to figure out the bits of this number. Okay, now these are 3 nibbles, 4 bits each, and 6 is that's 4, and that's 2 more. Whoops, 2 more. That's 6. 2 is that. Oops, one too many. And F. I'm assuming that you know binary and hex. And if you don't, then I would suggest you consult your local high school and ask someone there to tell you how all this works. Whoa. Okay, here's our number, and it has well, it could, with 3 bytes, you could theoretically have 12 bits, right? But this number has a maximum of 11 bits, so that's why this falls into the category where we don't care about this value, because we're only allowed 11 bits in this range. Okay, and these are our 11 bits. If you glue them together, that's 11 bits. 3, 4, 5, 6, 7, 8, 9, 10, 11. And this is where they go. 1, 2, 3, 4, 5. 8, 9, 10, 11. Alright? So let me just copy this pattern down. I'll show you how we map it in. These are our x's, okay? These are the x's. So there are 11 x's. The bottom 6 go here. Alright? According to this rule. That's what it says. It says the bottom 6 bits here and the upper 5 here. Okay, so we count off 6 bits. That's these ones. I'm going to just cut them out. Oh no, I'll copy. And I'm going to put them here. So those are used. How do I indicate used? Lowercase. I don't know. They're used up somehow. We stuck them in here. And now we've got 5 left, so let's go here. And now those are used. And I'll put brackets here to indicate. And another one of these little arrows, because are kind of useful. So that's all there is to it. That is the way you would do the encoding. Okay? And that matches this pattern. Here's our number in the brackets, and here's the 110 and then the 10 headers to these 2 bytes. Okay? So what is that number? Yeah, it's equal to, if we just get rid of the brackets, right? So that's an F. In hex, that's an F. And that's a. I should probably have gone the other way around. 8, and that's F minus 2, right? D. Is that correct? D plus 1 would be E, yeah. So D8, which is 1 byte, and AF, which is 2 bytes, and there's our encoded 2 bytes from what we started with, 62F. Alright, now that was easy because I was just putting them there by hand. But it's not that hard to do that in code. So I'll just leave it like this for now and try another one with our magic machine here. Let's try the next range. Divide by 8. There we go. 9DF. Now 9DF is bigger than this. 9 is 8. Whoops. 9DF. In binary, that's the 9 is that. D is, we just saw one, 1101, and F. Okay. Okay, so it's not in this range, and as you can see, it can't be in that range because 11 bits isn't enough. We need to grab this bit as well. So we've got to use the third range, and so we need to apply this pattern to our number. So I'll copy the pattern down. Put these underneath, glue them together. Oops. 1, 1, 0, 1. Okay, now again, the 6 of the bits go in the bottom byte. So that's, let's say, these 6. 1, 2, 3, well, not let's say, it's always in the bottom stack. So those are going to go in these X's. So keep the bracket too. Okay, now we have another 6 that go in here. And actually we've only got 6 left. So these go here. And there's an invisible 4 more zeros preceding this. And those go here. So that leads to E. This is an E0. This here is a 8 and 2 is 10, which is A. This here is a 7. Right? Add 1 to this and you get 8. This one is a 9. And the last is F. Right? So here is our sequence. So 9DF becomes that. 2 examples, 3 examples really. This, and the other one was some number, it was less, 1F, I think it was. This went to 1F. Okay? So I'm bringing these together. Now that's pretty simple, I would think, and you shouldn't have any problem understanding what I've just said. Now the question is just a matter of encoding it. How are we going to encode it? I mean, how are we going to run? This is great in that we can just, plop these things in here, but how can we make a machine that does this in a routine and predictable, fashion? Something we can just grind out these numbers with. Well, what we do is we just break it into cases, and then we've got to manipulate those bits. So we try to remember, keep the diagram. Let's see, I said this is going to be short. I think I've pretty much explained everything that you need, but I'll try and write that. Okay, very quickly, the encode. How are we going to do it? So, actually, let's get into main, where we can write it. We don't need any of this. We'll call this U. We'll give it this name. Now the way I defined it was this way. It's going to return a multi-byte sequence of 1, 2, or 3 bytes. And what I returned is probably uint, some number, but it's really only between 1 and 3, but it doesn't matter. Int is fine. Now, so it doesn't get confused with something else. What we want to pass into this thing is a wide character type, let's say called WC, and a buffer for the returned bytes. So we have a car, or byte, unsigned car, spelled correctly. Now I want it to be an array of bytes that has at most only 3. It can only be a 3-byte array. Okay, that's what that says. The reference to a 3-byte array of, an array of 3 bytes, and that's all we're allowed to pass into this function. And what we would like it to return is how many of these bytes will have valid values in them. Okay, so our loop is going to look like, we'll have an array of W cars. Say 100 of them or something. And I might have read in from a file. If I'm going to have a loop like constant. The position of the zeroth one, and then while just loop to 100 times. Up to 100, we're going to go from 0 to 100, to 99. I'm going to call this function. We're going to say int m bytes is encode pw. I don't have to use this. I can use this. And then we need a buffer. Don't even need to initialize it. Like that. And then we're going to output this many of these. So we would do fwrite to our file, b size 1 count number of bytes, pointer to file. See, that's the total. That's what we wanted to do. And that's the way I did it. I think that's preferable. You can't get lost here. It tells you how many bytes to write, and you have a buffer, and you write them out. Alright, now we just have to write in the function. First, the easy case. It's less than 8. That's from 0 to ff. In that case, the number of bytes, we're going to say bytes of 0 equals, let's say the low byte of WC, right? And we're going to return 1. That's it for that case. Only 1 byte to write. If WC is less than 800, right? Then it's in the second range. 0x. Okay, now we know what our return value is going to be. It's going to be 2. Now we got to figure them out using this scheme. So let's suppose we break up WC into 2 bytes. B0 or W byte 0 equals low byte WC one high byte. Right? Now we just got to take these 2 bytes and pack them in this form. So the first thing is, well, let's do this. We'll do the top or bottom first. We can do the bottom one first. We need to extract the bottom 6 bits from WC, and all those 6 bits are contained in WV0, right? So, bottom, right, 6 bits, that's going to be equal to WV0, and we want to just, and we want to knock out these 2, whatever might be in here. The top 2 are for the signature, right? 2 bits worth of signature. So we would like to AND this with the hex equivalent of 6 1, right? So that's 8. This number is what is that? F, the bottom, and 3, right? See how I did that? I just took 6 bits and broke it up into bytes like that. And I know that 4 ones is an F, and I know that 2 ones is a 3. So that's how we got the bottom 6. Okay. Now we need to add the signature. The top has to be a 1 0. So we want to OR this. Is that 8? That's 8. Yeah. These don't do anything because we're going to do an OR. Basically, and we don't even really need that. We need to, this whole thing is just 80, right? X. And so the answer for the bottom byte is that. Well, I can put it in bytes of, now that's not going to be 0 though. If we're reading it this way, this is the second byte, so this is the bytes of 1 is equal to that. Okay, that takes care of 6 bits. Now our number has at least 11 bits at most, sorry, 11 bits. And we've taken care of 6 of them. So that leaves 5 bits remaining in our number, right? Now, part of those 5 bits might still be remaining here in this low byte. So what we need to do is extract the top 2 bits, right, that we missed here from this part of the encoding. We're missing because of this. They didn't hand it away, and we want to get them back. So to get the top 2 bits, one way to do that is to just shift this value over by 6. If we shift this 6 this way, we end up with the top 2 bits in the lowest position, which is where we want them, because they're going to go up here. So the 2 bits from 0 equals, trying to go quickly, WB0 and shifted by 6. Right? Now we're almost done. Now, that means that there are 2 bits, right? in this variable. And there can only be 3 bits at most in this WB1 and at the bottom of its position. That's the way the scheme works, right? We don't have a picture anymore, but there's 11 bits, and so therefore this cannot have the 1 beyond the 3rd bit. So therefore, to make our 5 remaining bits, all we got to do is take this value, whatever it is, and shift it up 2 so it won't collide with this one. So we can't see it here, but whatever this number is, if it's, let's say, like this, right? We shift it up 2 and put zeros here. That leaves a slot to drop these 2 bits into. So what we do is we just take this second byte and we say the bytes of 0 equals this guy up to board with the result that we have here. Well, I can just put it in directly, right? So now we got that. I'll put it in brackets. But now we still got to add this part in. And what is that? That's an E0. It's a 3 ones followed by everything else 0, which is 3 ones is an E and 0. And that actually does it. Okay? And I'll leave it up to you to do the next step. That's the encoding. The next one I'll do the decoding. See you.